Welcome to a second video on triple integrals and volume. In the previous video we discussed how we can determine the volume of a solid region V by using this triple integral here, replacing differential V with dx, dy, dz, or any of the 6 possible orders of integration. So let's go ahead and take a look at another example. We want to determine the volume of the solid in the first octant bounded by x plus 2y plus z equals 6. Let's take a look at this in space first. The idea of this problem is to determine the volume in the first octant bounded by this blue plane. So the volume we're looking for would be the volume underneath this plane bounded by these 3 yellow planes. So our volume is going to be equal to the triple integral, where the limits of integration will be determined by the boundaries of the 3-dimensional region, and we'll integrate with respect to v, replacing dv with dx, dy, dz, or some other order of integration. So there's 2 main things we have to do here before we can integrate. We have to determine the order of integration and then also the limits of integration. The best way to do this is to look at the traces in the xy plane, xz plane, and yz plane. It's also important to recognize that there is often more than one possible order of integration, but sometimes one order will be easier than another. So to determine the xy plane, we'll set z equal to 0, so we'd have x plus 2y equals 6. So the x-intercept would be 6, and the y-intercept would be 3. And because we're in the first octant, we know that both x and y are positive, so the xy trace would be this triangular region here. Now for the xz trace, we'll set y equal to 0, so we'll have x plus z equals 6. So both the x and the z-intercept are equal to 6. Again, both x and z are positive, so this is the region of the xz trace. And then lastly, for the yz trace, x is equal to 0, so we'll have 2y plus z equals 6. So the y-intercept would be positive 3, and the z-intercept would be positive 6. So the yz trace would be this triangular region here. By looking at these traces, for the most part, we can use any order of integration. The only thing I notice is looking at the original plane, it's going to be easier if we solve this for either x or z. Let's go ahead and solve it for x, and therefore we'll integrate with respect to x first. This means that the limits of integration for x must be functions of y and z. So if we solve this equation for x, we'll have x equals 6 minus 2y minus z. That will be the upper limit of integration. And the lower limit of integration will be at 0 because we're in the first octant. Now we need to decide whether we want to integrate with respect to z first and then y, or y and then z. So we'll have either dz dy or dy dz. Looking at the yz trace, it's going to be easier if we solve this equation for z. So we'll have z as a function of y. So let's go ahead and integrate with respect to z second and then y third. So we must express limits of integration for z as a function of y. So z will go from 0 all the way to, solving this for z, we'd have 6 minus 2y. And then lastly, for y, we can look at either the xy trace or the yz trace. Notice that in both cases, y goes from 0 to 3. And now we're set to go. We'll first integrate with respect to x, which will just be x. So we'll replace x with 6 minus 2y minus z, and then with 0. That'll just give us 6 minus 2y minus z. We'll integrate this with respect to z, and then with respect to y. Let's go to the next slide. So now we're going to treat x and y as constants as we integrate with respect to z. So we'll have 6z minus z squared over 2, or 1/2 z squared. This will be minus 2yz. We evaluate this at 0 and 6 minus 2y. Let's be careful here. We just integrated the specs to z, so we're going to replace z with 6 minus 2y and 0. So we'll have 6 times 6 minus 2y minus 1/2 times 6 minus 2y squared minus 2y times 6 minus 2y. Now we have a bunch of algebra to do. So we'll have 36 minus 12y. Here we have to square this, so we'll have 36 times 1/2, that's going to be minus 18. And then we'll have a minus 24y times a negative 1/2, that'll be plus 12y. Then we'll have a positive 4y squared times negative 1/2, that'll be minus 2y squared. Then we'll have minus 12y plus 4y squared. Let's go ahead and combine our like terms. Looks like our constant term will be 18. Our y term will be negative 12y, or minus 12y. And then the y squared term will be positive 2y squared. Let's take this to the next slide. So we'll have 18y minus 12 times y squared over 2 plus 2 times y to the third over 3. So we'll have 18y minus 6y squared plus 2/3 y cubed. So now we'll substitute in 3 and then substitute in 0. So when y is 3, we'll have 18 times 3, that's 54, minus here we'll have 3 squared times 6, so minus 54, and then plus 2/3 times 3 cubed, that'll be 27 times 2/3, that'll give us 18. And then when y is 0, everything will be 0. So we have a volume of 18 cubic units. Let's go back and take a look at that graph. Again, the volume bounded by these yellow planes and this blue plane would be 18 cubic units. And that'll do it for this video. We'll take a look at another example in the next video.